In this chapter, we're going to discuss how to evaluate predictive performance of the methods and methodologies that we're going to discuss. And this is one of the most important topics of data analytics, because if we don't know how to compare a model to another model, then we won't be able to do any analysis at all. So why do we evaluate? So in the data mining process, we're going to consider several different methods for prediction. So when we have multiple methods, we should be able to compare the predictive ability of one model against another model. And also within a given model, there are some tuning parameters that we have to adjust. It may be how many periods we average or how many neighbors we select. Do we select one neighbor or two neighbors, 3, 4? So those tuning parameters need to be evaluated. And how do you evaluate? Through the performance evaluation measures. So multiple methods, and within a method, tuning parameters. And to choose the best model with best parameter, we need to be able to assess the performance of these methodologies and the tuning parameters. Alright, so now there are two types of outcomes that we will be predicting. Okay, so the target variable, the response variable, or the variable that we are trying to predict, it can be an interval target or it can be a class target. So if it is an interval target, which is a continuous variable, the outcome is numerical and continuous. So the predicted value is also numerical and continuous. So each observation we can compute an error measure by taking the actual value and subtracting from that a predicted value. So this would be the error in prediction. Now we can use this error for all the observations and then come up with a summary of predictive ability. So we'll talk more about that in a little bit. If it's a class target, then the outcome is class membership. So it can be binary, so in which case either yes or no. So the membership of a given observation in the yes category or in the no category. So that is the outcome. So the predicted value, when you apply a model for this situation, what we will get back from the model is a probability of class membership, and this is called propensity. So the probability that this observation will belong to the yes category. Okay, so that's one outcome that we get from our model, and based on that probability, then we have to assign a class membership to the observation. So there are two things here: probability or propensity, okay, and then based on the propensity, the class membership, and then we have to use these two concepts and come up with performance measures. Okay, let's first look at interval target. So interval target means the response variable, the y variable, is a numerical variable and it is a continuous variable. So we can come up with the error, okay, actual value minus the predicted value, and then using those errors we can come up with fit statistics, and these fit statistics measure the goodness of fit, how well the model fits with the actual values. So fit statistics can be used as a goodness of fit measures, or you can use that as predictive performance. We will look at the difference between these two in just a few minutes. What's the difference between fit statistics as measures of goodness of fit and fit statistics as measures of predictive performance? And then there is a third category of performance measure where we develop what are called lift charts. And lift charts are important when the objective is not really to predict the value of the target, but to be able to rank order the cases in terms of rank number 1, rank number 2, and so on, based on the value of the target. So if you're not, if your interest in rank is in rank ordering and not really the actual values of the predicted values, then lift chart would be the preferred performance measure. Okay, so evaluating the estimation error. So we already discussed this. Actual value minus predicted value. Okay, y minus y hat. So y hat being the predicted value, y being the actual value. That's your error. And the benchmark model for coming up with y hat is the average. So you can have very complex models, but if those complex models cannot beat the average value of y in terms of predicting, then that complex model is no good. So because taking an average of y and using that as our prediction is a lot easier, and a complex model should be able to do better than y bar. So as a predicted value. So y bar becomes our benchmark, and any model that we want to consider should be able to beat y bar in terms of performance measures. So here is the baseline. So if y bar is our prediction, then the errors will be y minus y bar. And if we take all those errors of all the observations in the data set, square them and add them up, we get what is called sum of squared error. Now this sum of squares of error, that is for the benchmark, that is when y hat is actually y bar, then we call that as total sum of squares. Total sum of squares is our benchmark. So that's the total variability in the data set, and we can divide by n minus 1, divide the SST by n minus 1, and we get the variance of the variable. And if you, of course, if you take a standard deviation, that's your if you take a square root, that's your standard deviation. So any model that we come up with should have a sum of squares of error that is smaller than SST. Otherwise, it's no good. Alright, so now let's look at a particular model. Suppose y hat is the predicted value of y using some model other than y bar. So then the error is y minus y hat. Then we sum the errors and we get sum of squares of error, and since we are considering only models that are better than y bar, then this SSE will have to be smaller than SST, SST being the benchmark. So the difference between these two is the amount of error that the model has explained. The model has reduced the error by that amount. So that is called SS model, sum of squares that is explained by the model. So SST minus SSC gives you the work that the model has done, the benefit that model has given, and you divide that by SST, the benchmark, then you get R squared. So that's your coefficient of determination. Now if there is zero SSC, the model has completely explained everything, then R squared will be equal to 1. So that's the best case scenario. Of course, it'll almost never happen, but that's your ceiling. You cannot have R squared greater than 1. Or if the model is complete crap, so that means SSE is actually equal to SST, so it has not done anything at all, then the model benefit through the model will be SST minus SST will be 0. So in that case, R squared will be 0. So R squared being 0 is the worst case scenario. So the actual value of R squared is anywhere between 0 and 1. Closer to 1 means the model fit performance is good, and closer to 0 means it's not good. And another measure that we can compute is to take the SSE of the model and divide by the degrees of freedom. So the degrees of freedom will vary. The baseline degrees of freedom is n minus 1. So that's when you use y bar, then the baseline degrees of freedom is n minus 1. But as you develop complex models, the more complex it gets, the less degrees of freedom you will have. So you will subtract more and more values. So if you add one variable into the model, then you have to subtract n minus 1 minus 1 for that additional variable that you've included in the model. So if you have p variables in the model, then the degrees of freedom will be n minus 1 minus p. In other words, n minus p minus 1. And use that here, and then you get what is called MSE. Then if you take a square root of that, then you get the standard error of y given the predictor variables. The x here refers to predictor variables.